efficiency savings that we need to be focused on. Okay, so the second area I talked about is the idea of substituting. So currently we're pretty dependent on petroleum, natural gas, and other petroleum-based or fossil fuel-based chemicals to produce food. In fact, you hear the phrase, we're essentially eating petroleum. Well, we're eating more natural gas than we are eating petroleum. But it's true. We're very dependent on it, not just for the fuel and fertilizer, but also most of the pesticides and things like that we use are basically petroleum-based. And yet we know that many of those chemicals can be derived from biomass just the same as they can be derived from petroleum, because biomass is a hydrocarbon, same as petroleum. And it's just a matter of figuring out what the chemical is, how do we get at it, and how do we use it. So kind of the next series of things I'm going to talk about, the reason that we got into it and the reason that we've been working on it is because the funding has been there around the issue of bioenergy. Everybody wants to produce ethanol and everything like that. So that's where the federal government is funding, and that's where we get the money to do it. So we've been working on these things, but at the same time we've also been thinking about, well, let's not just make ethanol. What else that's kind of neat can we make at the same time? And so we did this inventory. We started out in Eastern Washington, and at the time a postdoc did this, and he now works for me. He was working for another professor, and I stole him a couple months ago. But basically, he went out and he categorized all the different types of waste stream biomass that we have in the state. So this is things like forest slash mill waste, food processing waste, some of the ag waste, some of the crop residues, which I told him you can't call wastes, manures, and then another big one is the garbage that we throw away. And so his first study, 4.3 million tons of this waste in Eastern Washington. And he said, well, basically that's 40% of our electricity demand in Eastern Washington, residential electric. And then we went statewide, and believe it or not, Department of Ecology funded this. So, the first run through, we came out with 16.9 million dry tons statewide. Two things really jumped that number. One of them is the fact that it rains in Western Washington and we have forests, and that all the people live in Western Washington, so we have more garbage. But when you look at those numbers, and in fact we just revised that estimate up to 19.5 million tons because we got access to better data. That's equivalent to about 1.5 billion gallons of ethanol, which is probably 30% of our motor transportation needs in this state. It's a very, very, very significant resource. And this is kind of how it breaks out. Now the pie chart has changed a little bit, but I don't have an updated pie chart. Forestry is a little bit bigger than it was, but forestry and garbage, the organic fraction of municipal solid waste. So not the plastics and things like that you throw away, but anything that's organic in nature. So paper, food waste, all those types of things. And we throw away a lot of that stuff. Field residues, which I told Craig he couldn't count. We're going to count it anyway. Manures and food processing and packing waste. So we have a lot of stuff that we currently are not utilizing very well. In many cases, it's causing an environmental issue. So animal waste and many of our combined animal feeding operations are an issue that we need to deal with. And what Craig and I just did for another presentation is, we asked this question. So the state's really interested in carbon emissions, and we're really interested in fertilizer. What does that biomass resource mean? And we kind of took some really, it would kind of stab in the dark types of numbers in terms of, well, how much of that resource could we really theoretically get our hands on and utilize that's economical without, some of that stuff's way up in the mountains and you're just not going to get it. And we kind of came up with this number that removing about 20% of that total carbon that we're throwing away or not utilizing every year and taking it out of that cycle would meet about 10% of our state's emissions. So that's very, very significant. And then we looked at this other one, which I was really interested in, and that is, how much nitrogen do we have in that material relative to how much nitrogen we purchase as synthetic nitrogen in the state? This blew us away. So this is the amount in 2001 that we purchased in nitrogen fertilizers in the state. This is the amount that we have in that 19.5 million dry tons. will not find this anywhere in the world other than here, and maybe a few other places in the U.S. We have a lot of nitrogen that's out there waiting for us to capture and reutilize it. Now, the reality is a lot of it we're never going to be able to capture. But we have a couple of things like animal manures, food processing waste, and some of the municipal waste that are really low-hanging fruit, things that either are currently a problem that we pay to deal with, or that with a little bit of technology development and a little bit of investment we can actually turn. Okay, so let's talk a little bit about what kinds of materials these might be turned into. And I like to talk about these in terms of current generation and next generation soil amendments. And so current generation soil amendments are the things that you're probably most used to hearing. So compost, biosolids, manures, those types of things. They're good products. It's good to get them moving off the places where they're at and into production, because they're a source of nitrogen, they're a source of carbon and other nutrients, and they're a source of biological activity, which is a good thing. However, we don't know how they work a lot of the time. So sometimes you go get a load of compost and you use it and it does one thing. The next time you go back even to the same place, get your other load of compost, it does something different because it's different, has different characteristics. We have a really low threshold for where these materials are likely to go. Just because, you know, I'm not going to take the risk, if I'm a potato grower, of getting my load of potatoes rejected at the processor because I brought in a worm with compost. Same thing with tree fruit production. You know, I bring in the compost, there's nitrogen in there, but I can't control how that nitrogen is released and what the curve of the release is. So I may have nitrogen when I don't want it and it's ruining my fruit quality. So there's a pretty limited market for this material, and what we've kind of talked about in our group is if we're going to really see products or materials move from our waste stream back into agriculture, we need to have much more reliable products. And this is the kind of thing I'm talking about. So next generation soil amendments. Keys are we have consistency and reliability, predictability, and precision. We know how these materials are going to work every time we use them. Well, we don't know yet, and some of them we're working on. Potential to hit some of these other markets, you know, potatoes are worth so much more, spinach seed, sweet cherries, greenhouses and nurseries, trying to hit products that can actually substitute for things they currently use that are high dollar, high risk materials. We think we can get there with a number of materials, and so we're doing some interesting work. Biochar, recovering fertilizers from manure. We've developed a process essentially as a potting substrate replacement for peat moss, which is a pretty big environmental issue, and brassica seed mills, which I'll talk about in just a moment. So this is probably the biggest area of our investment, is in terms of nutrient recovery from some of these really low-hanging fruit waste, primarily manures and food processing waste. There's a lot of nitrogen in it, a lot of phosphorus in it, and some other waste too. So we've gone through about 8 different types of technology to remove phosphorus, a couple different technologies to remove nitrogen, and in fact we think we're getting pretty close, and we'll have a report out in about 3 months that kind of captures all the work that we've done. But we're pretty confident that we can get about 70% of the nitrogen and phosphorus out of manure at a relatively reasonable cost. Gets it off the dairies where we don't want it, creates a product that is predictable, that we can sell back into agriculture, and it's biologically based. And this is some of the work that we're doing. This is one of the phosphorus recovery technologies. This is some